What we have seen with this example of calculating the pH of the rainwater is all those equilibrium constant calculation, all those solubility constant or acid dissociation are real equation. You can play with it. And this is the core of the CO2H2O system. You can work with any system, of course, but this is the system we're working with now, is the CO2H2O system. So again, when you have a body of water in natural environments, you will have a certain amount of CO2 dissolved in it. So the CO2 that is under the form of gas will dissolve into an aqueous form. And this aqueous form will form the HCO3 stars, which is carbonic acid, the bicarbonate, and the carbonate ion. Okay, and this, of course, this is a star because it's counting this aqueous plus this molecule of combining water and CO2. And this is what we call the dissolved inorganic carbon. Very important for the carbon cycles, DIC. You may have heard about that in other classes. And this is what it is important to calculate and to have an idea about the repartition of those different species into a natural body of water or into your lab when you're doing some experiment. You can measure it, or you can also calculate it through those equilibrium constant. This is what we're going to do right now. We're going to build a plot telling you as a function of the pH, how much of those different species of carbonate you will find into a natural body of water. So again, just to be sure that you understand that when you're writing, even the first one knows the CO2 gas giving you your CO2 aqueous. This has what we call the key CO2, the constant of solubility of CO2 into the water. You can call it the Henry's constant if you want, equal to the activity or concentration of CO2 aqueous divided by the PCO2, the partial pressure of CO2. This is the partial pressure of CO2. This is one equation you can play with. You can rearrange that to calculate what is the PCO2 as a function of the concentration of aqueous divided by this constant. If you know the constant, you can calculate the PCO2 if you know how much CO2 you have into your water. And so you can rearrange those equations and have as many equations you need to solve a specific question. You want to find a pH of solution, you want to find the amount of bicarbonate, the amount of carbonate inside the solution. This is how you're going to work. Again, this is the first equation. Second equation, we're going to write this many times for you to be confident with that. The CO2, the carbonic acid, will give you your famous bicarbonate plus H plus with a Ka1 value that is equal to HCO3, the bicarbonate concentration, times the concentration of H plus divided by the concentration of carbonic acid in your solution. Here you can rearrange that by dividing by H plus, so we have Ka1 divided by H plus equal the concentration of bicarbonate ion divided by the carbonic acid. So here you have a direct relationship between the amount, the quantity of carbonic acid you have in your water and the bicarbonate as a function of the Ka and the H plus. And the H plus, if you're taking minus the log of it, you will have a relationship with the pH. And this relationship here is very important. What it's telling you is if Ka equal H plus, if Ka1 equal the concentration of H plus, that means that HCO3 minus equal the H2CO3 concentration of carbonic acid in your solution is equal to the amount of bicarbonate. This will be equal to 1 because those two values are equal. You can actually use this formula to calculate some very interesting ratio in some solution. And now we will just try to make a small example, and then we will build a diagram called the Bjerum plot. It's pretty difficult for me to pronounce it. This is a Swedish term that will give you the repartition of the DIC species, the various DICs, the carbonic acid, the bicarbonate, and the carbonate, in a body of water with a known, with what we call a closed system, with a known amount of DIC into your system. So again, if I'm taking this rearrangement here that I just calculated here for the carbonate, the bicarbonate carbonic acid, you can actually have the same for the bicarbonate and carbonate. So again, if I have Ka1 equal, now remember that the concentration of HCO3 minus times the concentration of H plus is activity if you want, but I'm going to deal with concentration right now. HCO3, the carbonic acid, and you have Ka2 equal the concentration of carbonate times the concentration of H plus divided by HCO3, the bicarbonate. I'm rearranging that, so Ka1 on H plus equal the concentration of bicarbonate divided by the concentration of carbonic acid, and Ka2, the second constant, the dissociation of bicarbonate into carbonate again, divided by H plus equal CO3 2 minus the concentration of carbonate divided by the concentration of bicarbonate. So now I'm taking the log of everything, log of this. So in this case you will have log of Ka1 divided by H plus equal log of Ka1 minus log of H plus. You know that the log of A divided by B equal log de A minus log de B equal the log of HCO3 minus divided by the carbonic acid concentration. And so you understand that this is the pH, and if I'm moving that here, it's going to be minus log of Ka, it's going to be the pKa. So you can rearrange that by writing pH equal pKa1 plus log of the concentration of HCO3 minus divided by the concentration of carbonic acid. So now you can work with that, because you can do exactly the same. This is for equation 1. You can have the same equation. pH will be, you can do that yourself, will be pKa2 plus log of the concentration of, in this case, carbonate ion divided by the concentration of bicarbonate. You can do the same calculation here by putting the log of this equation here. So what those equations can tell you? They tell you that when, in this case, pH equal pKa1, if the pH of the solution of your water, body of water equal the pKa1 of the carbonate, which is dissolution of the carbonic acid, this value, the amount of HCO3 minus, must be equal to the amount of HCO3, the carbonic acid. Okay, because this has to be the log here. Let's take another color. The log here has to be 0. So this has to be 1. And if pH is smaller than pKa, okay, I mean this value is smaller than this one. So this one is bigger than this one, though. This log part here must be negative, because this pKa1 is bigger than the pH. So to have this equality here, you have to have pKa1 minus something. And the only way to have log of something that is minus, that means that this has to be smaller than 1. So in this case, if you have pH smaller than pKa1, you must have HCO3 minus divided by H2CO3 smaller than 1. That means you have more carbonic acid than bicarbonate. And if your pH is larger than the pKa1, this log must be positive, larger than 0. That means that this ratio of bicarbonate on carbonic acid must be larger than 1. That means you have more bicarbonate than carbonate. So for pKa1, and this is a pH, if the pH is exactly equal to your pH or your pKa1, you have equal amount of bicarbonate and carbonate. If you are pH higher than the pH pKa0, you have more bicarbonate. If the pH is smaller than the pKa1, you have more carbonic acid than bicarbonate. You can do exactly the same for this pKa. When pH is equal to pKa2, the two species carbonate and bicarbonate are equal, have the same value, because this has to be equal to 1. If the pH is smaller than pKa2, you will have more bicarbonate. If the pH is larger than pKa2, you will have more carbonate. And for pure water at 25 degrees, again, pKa1 equals 6.33 and pKa2 equal 10.33 something. So you understand that now. You know that if you're measuring your water, if you have a body of water, you're measuring the pH. If your pH is exactly at this value here for your body of water at 25 degrees, 1 atmosphere, you know that you have exactly the same amount of bicarbonate than carbonic acid. If you have a pH that is 10.33, you know that you are at the pKa2. That means you have exactly the same amount of bicarbonate than carbonate. If you have in between those two pH, you are mostly bicarbonate. If you are lower than this pH, you will have mostly carbonic acid. And if you are higher in terms of pH than this value of 1033, you will have mostly carbonate ion. And you can actually plot that on the graph and calculate the repartition of the distribution of the concentration of those different species as a function of the pH. And this is what we're going to do right now. This is a summary slide about the relationship between the bicarbonate and the carbonic acid, as well as the bicarbonate and the carbonate. This is a rearrangement of those equations. This is coming from the dissociation constant of carbonic acid in this one, and in this one, the bicarbonate functioning as an acid. Bicarbonate, you'll see that, can function as a base or an acid. If you are in the key 1 value pH range, the bicarbonate will act as a conjugate base. If you are in the range of the key 2 value for the pH, or the pKa2, the bicarbonate will act as an acid and give a proton away to water. This equation shows that, of course, if the pH equal pK1, when I'm saying pK1 here, I'm simplifying, is pKa1, because you can have pKb, you understand that. You can have the same calculation for the base. We're focusing on acid right now. So pK1 equal here pKa1. the activity of carbonic acid and bicarbonate are equal. And the same here, for pH equal to pKa2, the activity of bicarbonate equal the activity of carbonate. So now what we can build is what we call a Bjerum plot, or Bjerum plot if you want. Don't need to know this name, just a plot of a partition. So what is important here? We are going to work with what we call a closed system. So the closed system is you're not exchanging matter but energy with the surrounding. Okay? So an open system, you exchanging matter and energy with the surrounding. A closed system, you only exchanging energy, no matter. And the isolated system, you don't exchanging anything. So in this case, that means you don't have exchange between the atmosphere and your body of water. You have a body of water that is sealed, separated from the atmosphere. That means you have a certain amount of DIC inside. This is your constant. The total carbonate concentration is fixed. This is very important here. You want to write it a different way. The DIC is constant, is known. You have seen that in an open system, the DIC can be calculated because it's in equilibrium with the atmosphere. In this case, you're not necessarily in equilibrium with the atmosphere. It is just a body of water that has a certain amount of dissolved CO2 into the water. You can think about, for example, groundwater. Groundwater is not in equilibrium with the atmosphere. You can dissolve limestone in the surrounding. You can have a lot of CO2 in this water because you are a cold system, and maybe higher pressure. And you've seen that the value of the Henry's law increase with those type of variable. That means that you can put more CO2 into your system when you have a colder water and also a higher pressure. So this is very important because we will calculate for an open system in the following slides. But now we're focusing on the open system. In the closed system, the known species are the carbonic acid, the bicarbonate, the carbonate, the proton, the H+, and the hydroxide ion. What we're going to use is what you just calculated before. For each pKa value, you know that the acid and the conjugated acid and the base pair are equal in concentration. For pH smaller than pKa1, you mostly have carbonic acid. When the pH is in between pKa1 and pKa2, we just calculate that, it's mostly bicarbonate. And if pH is larger than pKa2, you have mostly carbonate. So how do you calculate that? Using exactly those different equations, and you have this type of plot here. So this is a Bjerum's plot here for a DIC of 10 to the power of minus 3 mole per liter. This is your data. And this is what you're going to see here. Okay? This is what you see here is your value, because this is a log scale of the activity of the various species of carbonate. So the log scale is just showing you not minus log, but log, okay? The log of 10 to the power of minus 3 is minus 3. So here you are in pure water. That means that this is a pH equal to the pKa1 of the carbonate system, and this is a pH equal to the pKa2 of the carbonate system. So here you have a limit here. Here you have domination of carbonic acid. Here you have domination of the bicarbonate. Here you have domination of bicarbonate, and here domination of carbonate. This is exactly what you're seeing here. This is the repartition of, let's do that in color. Red, this is the distribution of the carbonic acid. This is the distribution of the bicarbonate, and this is the distribution, or let's do that in green, of the carbonate here. It's not very brilliant. Let's do a blue for bicarbonate here. Here you go. So don't let you fooled by the fact that this value is really high on the y scale here. This is 50-50 because this is a log scale, okay? If you're taking 10 to the power of minus 3 divided by 2, you will have this value because it's a log scale. If you will not have a log scale, this point here will be halfway down there, okay? We have another graph showing you later. So don't let you get fooled by this log scale here. This value is 50-50. 50-50 between carbonic acid and bicarbonate, and here 50-50 between carbonate and bicarbonate. So again, pH that is, in this case here, smaller than this pKa one, you have mostly carbonic acid. In between those different things here, you will have mostly bicarbonate, and pH above 10.33 you will have carbonate. The pH of the main body of water on the earth are situated between 7 and 8. Ocean water is around 8, tap water 7 to 1.5. So you understand that the main form of DIC into the tap water or inside the ocean water or any river will be bicarbonate. And this bicarbonate will play a very important role in the buffering of the system you're working in or you're living in. So close to 99% of the DIC into the water of the tap water you're using is bicarbonate. It's not carbonate or carbonic acid, it's bicarbonate. So here, as a function of the pH, you are able to determine which species in the DIC should be dominant in your body of water. This is very important. Let's take an example here of a closed system and a question you can ask. You have a body of water in a closed system. You want to know what is the PCO2 inside this body of water. Again, this is not in equilibrium with the atmosphere, so we know if it would be in equilibrium, the PCO2 would be the partial pressure of CO2 in the atmosphere, but it is not the case. This is a closed system. So you want to know what is the phase of CO2 under the form of gas that you can have in equilibrium with this body of water. To do that, you're going to play with those equations. And here is a summary slide that I will just add a couple of steps to be sure that you understand that. This is the final equation you will use. But to go there, what we have is equation for the K1 value. What is missing here is equation for the equilibrium of CO2, which we know is equal to the concentration of carbonic acid divided by the PCO2, and this is the PCO2 you need to calculate. Okay? So what you're going to do is solve this equation here for carbonic acid, CO3 equal KCO2 times the PCO2. Then, of course, you understand, it's pretty simple. You're taking this value here and you're replacing that in this equation. That means you will have something that is K1 equal concentration of H plus bicarbonate divided by the PCO2 times the KSO2. And now, of course, you're shifting this value with this value and you're getting this equation here. And then you're taking the log of this equation, so you have the log of that. Why are you doing that? Because you want to express that as a function of the pH. So now you have, this is the pH you can measure in your system. This is the bicarbonate you can also measure in your system. Those are two constants that you know for a specific pressure and temperature. So you can calculate the PCO2 you have in your system. Let's take an example here. of calculation. An exercise with a groundwater sample has a pH of 6.84 and a concentration of bicarbonate of 460 milligram per liter. You know that at this pH that is close to neutral, the main form of DIC will be under the form of bicarbonate. So we will not care about other form of DIC such as carbonic acid or carbonate. What is the PCO2 at 25 degrees? And to do that, you're going to do simple things. What you're going to do first is to convert those milligram in mole, because when you're dealing with the equation, those equilibrium constant, you will always work with molar, mole per liter, not milligram per liter. You need to be careful with the unit. So the first step would be, taking the white again, to have 460 milligram per liter. 1 mole of HCO3 equals 61 gram. You can check that on your periodic table. The molecular weight, the weight for H is 1, carbon is 12, and oxygen is 18. So 3 times 18, 48, but 12, 60 plus 1, 61. This is per mole. What you have is milligram. So if you want, this is, in this case, 0.46 times 10 to the power of minus 3 gram per liter. So this will give you a value of, in our case, of 7.54 times 10 to the power of minus 3 mole per liter of bicarbonate in your water. This is what you're going to use. And then you're going to use the equation that we just saw here, this one. It's a bit messy here. So what you're going to have is the log of the PCO2 equal minus the pH plus the log of the concentration of HCO3 minus the bicarbonate divided by two constants, the Ka1 and the KCO2. You know that the KCO2 from literature from previous slide is equal to 10 to the power of minus 147, and that the Ka1 at 25 degrees pure water, 1 atmosphere, equal 10 to the power of minus 635. So that's, we know. We just calculate. This is your HCO3 concentration in molar. The pH we know, so we can calculate that. It's pretty easy. So at the end you will have, in this case, minus 6.84 plus the log of, in this case, 7.4 times 10 to the power of minus 3 molar divided by 1047 times 10 6.35. This is what you have, is basically 10 to the power of 7 minus 7, we're adding those two, of course, 82, and this will result in the final calculation as 5.69, and the total will be minus 1.14. If you do the calculation, I'll let you do the calculation with machine. So you're taking this divided by this divided by that, then you're taking the log of it, you're reaching this value here, and you adding to this pH value, and you're getting that. And this is the log of the PCO2. So the PCO2 in our case will be equal to 10 to the power of minus 1.14, which is way higher than the atmospheric partial pressure of CO2, which is around 10 to the power of minus 3 in our case, if you want to take an average value. So in this case, the groundwater will have way more bicarbonate in solution than a water that will be in equilibrium with the atmosphere. That's a nice exercise to do that. This is what we define as a closed system. Let's have a look at what we call an open system now.